Thank you. Is there any pointer that I can? I don't have.
No.
No. Okay. I'll point with my finger and then. Okay, thank you. So my talk is going to be very different from the previous one from Moshe's, and I'm going to talk very much about robot vision and applications of different types of vision-based algorithms for guiding robot control. However, even if we didn't meet before, I'm really happy to basically start with the same image as you. It's a drawn image of a phone. I hope everybody sees this as a phone or a picture of a drawing of a phone. Yes, no?
That's the iPhone.
You did like iPhone 6. Okay, good, excellent. Seems to be an interesting object to dwell on. So it's a phone. However, to a robot that is given the task of interacting with this phone in different ways, there are different parts of the phone that should be or are of interest. So give me the phone. We would like the robot to understand the phone as a whole, segment it from the background, be able to estimate, for example, its pose and so on. So to interact and grasp it, the preferential segmentation would look something like that. Now, if the robot is asked to turn on the phone, it should somehow, by miracle, understand that there is a button on this specific phone, on this iPhone 6 or 7. It's on the top. So the robot should be able to attend to a part of the object. And if that part is not visible, this information should somehow come to robot, either because it has manipulated the object before, or because there is a human or somebody else helping the robot to find that particular feature or part of the phone. Now, if the robot is to dial a certain number, then there is again another part of the phone that is of interest. So either you use the keyboard or maybe you interact directly with the screen. So the notion of objectness, or what the robot understands as object or its functional part, depends very much on the task or action the action is expected to perform. And this is also something that we heard a little bit in the talk before. Now, phone might be a relatively easy object to find, to detect, to label its parts, and so on. It's not completely trivial because the turn on and turn off buttons are at different places. One of the phones that I have, it's actually on only the screen. The keyboard is hidden, and it needs a pretty complex action of actually turning the keyboard out. I don't know if you know which phone I'm talking about. So I'll demonstrate. So this one, I have also iPhone, but anyway, so this one is much more difficult, right? Because the robot needs to actually apply a very, very complex action that we apply without thinking and then find the keyboard and so on. So how this contextual information or more symbolic information is stored in objects in computer vision community commonly does not exist, right? So most of these things need to somehow be stored only for the purpose of acting on objects, and this is what we do in robotics. Now, there are more interesting images to think about and more interesting and more difficult scenarios that we might envision, such as asking a question, what do you see in this image? Shoot, 2 airplanes. Yeah. You need to get glasses.
The
the robot company. No, my orbital frontal cortex should be inhibiting my social network more.
Okay, good. Well, maybe there is a cure. Okay, good. So what do you see in this image? It's a sculpture. It's two sculptures that are human-like, two humans talking. I don't know. There are like many different explanations of this image, and I think that why we would get different explanation from different people is that it's very much dependent on whether you have seen this before, maybe if you have been to the museum and even touched it, or look at it from different sides and so on. So the question is, if we would like a robot to explain this image, and if we would like it to find some functional aspects of that image, so parts of image that look like something it has seen before, the question is, of course, what to represent. So what are the features in this image that one would need to extract in order to, for example, get an answer that these are two human-like features or sculptures that are facing each other, talking to each other, and so on. Now, thinking again about face recognition and about the current state of the art in computer vision community, finding faces in images, it's very easy, right? Your mobile phone camera can do that. So there is obviously a very easy way of defining features that are task related, where the task is finding faces in images. And to my understanding, it's easy because there is very little variation in images, right? In faces. Most of the faces looks very alike, two eyes, nose, mouth, and so on. So it is very easy to define or model very dedicated features that are able to find what discriminates facial features from most of other things in the environment, or most of the other things that a robot or a human may account. Now, the other thing is the interesting aspect of global versus local information, right? So if you look locally, and looking locally would be making a small window with your hand and just peeking through that window and parsing it over the image. Now, when you do that, it gets even more difficult because there is nothing there that you will see that is face-alike or body-alike. So apart from using visual feedback to understand these images, we're also using the notion of the global aspect, so how these small individual features relate to each other when doing decision about objects. So I'm not a neuroscientist and I'm not a psychologist, so this is maybe what Moshe was saying now for 2 hours before me. But what we see depends on how we look at things. And how we look at things may also depend on what we are supposed to do. So we have a plan. We act dependent on what we are supposed to do and so on. So very much this contextual information or the top-down information that guides our visual processing depends on what we kind of look for. And this is a little bit different from how most of the current computer vision algorithms or methods work, and I will try in my talk to shed a little bit of light upon those. Now, my research is in the area of robotics and what might be meaningful tasks for a robot. It might be robot pick up this cup, robot bring me my cup, robot remove this, robot fetch me something to drink from, clean the dinner table, and so on. And these are very simple, right? Most of these we execute as humans. Frequently when interacting with the environment, and it feels like that we do this even without any significant mental kind of, let's say, energy using process. So most of these things we can even do without using our visual information continuously. So at some point I have put this bottle on the table, right? And in order to interact with it, I don't even need to update my map or look again for where it is. So I will use or apply some gross motion of my hand until the contact with the bottle has happened. And if I do wrong, I will use my tactile feedback in order to do the correction. And this is approximately how we would like or how we need to implement processes in robots that are supposed to do similar things. Now, one of the things, or one of the reasons, is not that we don't need to do it in terms of not needing to update the map or so on, but we are actually forced to do it in cases where the uncertainty is significant. And the uncertainty can come from very many different things. It can come from the fact that the lighting changed in the room. It can come from the fact that the robot's odometry is not good. It can come from the fact that the camera is not calibrated and so on. So the uncertainty affects very much the process of where we think the things are and where they usually or where they actually are in the environment. Now the robot that, or the movie that I have played is just a simple robot moving about in the environment, and what it does, it has a laser and it has a camera, so just builds a map of the environment very easy, it detects where the walls are, and then it detects some interesting images that has seen before, so it has images of those, so the only thing the robot tries to do is to generate some statistics about where these objects are usually placed in home-like environment. And why is this important? Well, the statistics is important because once the robot is given a task to fetch something, it can remember where it most commonly sees it or detected it, or where it saw last. Now that's easy. Robots can move around, they can detect obstacles, they can avoid obstacles, they can detect things that they have stored in their memory and so on. Now a little bit more difficult thing for a robot to do, let me see if I can do this, if not, no, okay, so we will do it like this. So, okay. Sorry, I have a problem with the resolution, so I'll just need to run my images manually. So, a task like this, which according to my husband is even difficult for some humans. Washing dishes. Now, why is this so difficult? And I know that this is not something that we do maybe as frequently anymore as we did. We just tend to put things in the dishwasher. But from time to time, we do tasks like this or similar ones. So what do? We pick up an object, in this case a sponge, which is far from being rigid, and we mold it and change its shape by using a single hand in order to be able to interact with another object. Okay? And we do it differently for different objects. We use two hands, and there is contact from time to time. There is no contact, and so on. And apart from using the right hand as a tool, really, in terms of just sweeping the objects and cleaning them, from time to time the hand is also, and the sponge in the hand is used as a grasping body. So basically, what the hand is used for. There are many different types of activities or actions the hand is performing, and most of the degrees of freedom, I would say, of the hand are used in a task like this. Now, there is currently no robot in the world that can do that. What is even more alarming is that there are actually no hands, artificial hands, in the world that can do that. And when I say artificial hands, I mean both robot hands in terms of the dexterity and the degrees of freedom, but also the prosthetic hands that can be bought usually have only single, maybe 2 degrees of freedom, and doing things like this is basically impossible. So what we compensate with is that we compensate with the arm motion, right? So what we can't do with the hand, we try to do with the arm. Now think about a robot that is supposed to look into many sequences such as this one. So basically generate lots of data, and this is what we currently do both in computer vision and machine learning, so data-driven approaches. So generate lots of example sequences and then build some form of a model of how things are usually done or executed, and then transfer that to its own body. Okay, that's a viable approach. Learning by demonstration has been used for quite some time. Now the difficult thing is what matters in a sequence like that. Is it really the way the sponge and the object interact with each other, or is it really the way the human moves his own hand? The other approach is more developmental, so no looking at humans, but trying to generate or trying to learn a model from scratch that somehow goes or brings a robot from a dirty plate to a clean one. How does the robot then get some form of a reward while learning this process in order to understand that, well, it shouldn't be breaking the plate, it should be really sweeping it, and so on. So it's difficult. And the examples that I'm going to give you in the remainder of the talk address both of these aspects, so learning from humans and then also learning more in a developmental way. Now, going back a little bit to computer vision and the question of what to represent, and going back to 70s, there is a big gap between the categorical model, so the notion of a bottle, and what is really being extracted or represented in an image. So in the beginning of the research in computer vision community, people have worked with very idealized images. So no noise, no background clutter, a single image on a very simple background, and so on. And they were working on developing methods that basically relied or tried to find a one-to-one mapping between the representation and the extraction, what can be done from images, single or stereo, and then link that to more categorical model. Now, as we go on and come to recent work, more and more of the approaches are data-driven. So everything is about taking as many images as you can and then trying to develop the machine learning method or the classifier that is somehow going to, let's say, answer a question of whether there is a bottle on the table or not. But the problem is that there is a significant gap between really understanding what a bottle is and what the functional attributes of that bottle are. So what can we do with it? So we can use images, 2D images, and we can have some very dedicated features. Again, think a little bit about finding faces. What we can do is we can find areas that most likely are occupied by the bottle, but there is nothing in the model that is in a way categorical in terms that it tells us, well, that bottle can hold liquid, or that bottle, so you need to be careful when you pick it up. The bottle can be both rigid and it can also be deformable, so made of plastic. The bottle can roll, so if you want to give it to Andreas and the tap was on, you can maybe, rather than throwing it, you can actually roll it. So yeah, there is lots of information there that we cannot, again, currently with this amazing computer vision methods, really encode easily. It gets even more difficult, so think a little bit about this. Let me see if this plays. Very simple action of opening a book. Hopefully it will play again. No? Okay. Hello. So what the human does, it approaches a book, a very known machine learning book, and just opens the cover. On the second image, the scene is more or less the same. But what a human does, it takes another book or a notebook and covers the machine learning book. Now you don't see the end of this sequence, but visually these two, after opening the book or putting another book on it, tend to be very, very similar. Now in this case here, what a human does, it also opens a book. It's a different book. The end result doesn't look anything like this, in this case here, and I'll play it again. The human did it with 2 hands. So what is in the structure of this sequence that a robot should learn and represent? What is that is making this, how can we extract visual features that can basically say to the agent that, well, these two are the same. And what you should be actually learning about is this kind of rotational motion. And you can do it with 1 hand or you can do it with 2 hands. So the objectives would be going from a very targeted processes of detecting things, avoiding things, grasping things, manipulating things, structuring and molding things, because this is what we currently do in robotics, to learning all these processes. And learning these processes, again, one way of doing this is to be inspired by humans' way of executing things, so learning from humans. So having this learning by demonstration approach, or trying to do things by its own. So the robot using its own body to understand the causal aspects of action, so the effects of certain actions. What I think also needs to be kept in mind is that the body of the robot in most cases will be very different from human body. So there will be less degrees of freedom and so on. So the way that the robot executes an action might be very, very different from what human does. But this is also what we again see in human activity execution. For example, when one of the fingers or the hand or something like that is injured, we have the ability of vary different types of body and compensate for those parts that have been, for example, injured. So our bodies are very redundant, and in most cases, robots' bodies are not. They have just enough degrees of freedom to, for example, 6, to, let's say, access a certain point in the environment with the particular orientation. So that's the bare minimum. And there are few arms in the world, or, well, most of them are 6 or 7 degrees of freedom, compensating just for the redundancy in the wrist, but everything else is very low dimensional. Now, looking at a scene like this, what do? You part it with your eyes. You attend to certain parts, dependent a little bit on how hungry you are. You maybe look at a certain package a little bit more time. You get angry with me because now I reminded you that you are actually hungry and you really have some craving for sweets. Andreas, maybe not you. But what is interesting here is that by, again, very fast we can count how many objects there are in the image. There will be a little bit maybe of a problem with those MMMs or whatever they are called, the jelly sweets at the bottom, because it's that one object or many of the same kind and so on. But even if we are asked to interact with the scene, we also have the ability of seeing beyond the image, right? So even that many objects are occluded and so on, the fact that we know something about the objects from before, or we have different processes in both eyes and brains to help us to imagine things beyond what we see, this is not so very difficult task. Now, for a robot that is supposed, for example, clean the dinner table, so remove all the objects one by one from the table, we might be taking a very classical approach. What would that be? We would perform some form of object recognition. So hopefully somebody has built a big database of these objects or examples and told us, okay, this is how the sweets packages look like and so on. We will detect the individual instances. We will try to do some pose estimation, not very easy for objects that are deformable, but let's say we can have a good idea approximately where in the 3D these are. We would perform some grasp planning, and grasp planning would be both taking into account the fact that we cannot reach all the parts because they are, or all the objects because they are occluded by other projects and so objects and so on. We would perform some visual servoing, so vision-based control to reach a certain point in 3D, and then perform some grasp execution. It's really interesting to see. I think that, well, I started my research in 97. This is when I started with my PhD. And I felt that, wow, visual servoing has been something that people have been doing since like late 70s or early 80s. And it's still not a solved problem. So at conferences, robotics conferences, control conferences, that people are still addressing visual servoing. And what is visual servoing? It's moving your mobile robot or your arm from point A to point B in order to fulfill a certain requirement of being in a certain relative pose with respect to the object. And most of the approaches, what they assume is that the starting position is known, and that by, again, some magic, you know the actual pose between your hand and the object you're supposed or you are visual servoing on. And in order to be able to do that, you of course need to have the model of the object. Now there are some variations on that, but that's the bottom line in the approach.
So Danica, you're saying visual servoing and possibly these other stages turns out to be so hard because also of their interdependencies. Is that the key point here?
Well, I mean, in visual servoing, the problem is really relating more to the optical flow and the motion flow, right? So that if you are using only a single image, you will not see a difference between the translation in this direction and the rotation around this axis. So the image Jacobian matrix that you use for control, it's not a diagonal matrix, right? So you can't design a control algorithm that will be able to separate just based on the visual cue from the image these degrees of freedom. So maybe you want to do translation in one direction, but maybe you're doing translation in one direction, but you should be actually doing the rotation. So there are still theoretical problems in some of these aspects in order to define the control, the right control in order to be able to execute stably these processes. Grasp planning and grasp execution, I have them as two things, because grasp planning is very much about how to, what kind of posture to use for the robot hand with respect to the object. And human hand, well, it's more than 20 degrees of freedom. Some people say 25, some say 27, some say 24, and so on. It's redundant, and most of the joints that we are using in the hand, they are also coupled. So the actual realistic degrees or level of the number of degrees of freedom of a grasp is not all that high. But most of the hands do not have 5 fingers. Most of the hands only have 2 or 3. So the space of potential grasps is smaller, so what they can achieve, but it's still infinite, okay? Why is that? Because if you take an object like this, and even if you have only 2 fingers, you can grasp this object in infinitely many ways. Not all of these are optimal, and we know that, right? Because what we are trying to do, based on our experience and based on, I don't know whether we have a physics engine in the head, I don't think that we do, but we know that, well, it's a bottle and it's filled with water, so I should probably not be applying my grasp here because it will rotate, okay? And I should probably not do like this because it's too heavy and it will slip because there is not enough force in the fingers. So what we are trying to do, we are trying to apply optimal actions, but that's not enough. What we are doing, we are applying actions that also afford the subsequent task or the subsequent action we plan. And this is also something that we have heard in the talk before. So if I'm about to drink, I will probably do something like this. I will most likely not do anything like this. If I'm to put or fill the glass with the water, I will again do something like this. But however, if I'm to just move this bottle from A to B, I will not bother of using my whole body and come to a position to actually be able to do that. I will do a little bit less energy consuming thing and just move it like this. And where is that knowledge coming from to me? So again, this is something that current grasp planning algorithms are still not taking into account, so the subsequent task. So most of the grasps that are being generated just for picking an object up. Yeah, so I'm not going to dwell very much on this. I think that you can still read in major conferences of computer vision papers about techniques for object recognition and pose estimation and so on. But what is really important and what goes back to what Paul has asked me is that most of the people are actually addressing this problems in isolation. So the technique that is maybe optimal for solving the object recognition problem is not necessarily optimal for using as an input to the subsequent process of pose estimation and so on. So visual servoing has in most cases been only about has mostly dealt with the problem of reaching a certain relative position with the object. So let's say I start here and I move my arm or hand to come to here. Now, if somebody was not thinking through or not being so very nice with putting these bottles in this way, I might have ended up with something like this. So the robot can still try to execute the visual servoing in terms of basically moving the arm from here to here. But in the process, a collision will happen. And this is just because the whole scene is not taking into account. So yes, I would say that there are, yes to your question, I think that one of the problems is that these aspects or these problems are still considered in isolation, and you can write still very nice papers about the methodologies of solving each of them, but not necessarily still be able to do something like this, which is about, let me see if I can do that, and then that. No, okay, then we will do it like this. Equipping a robot with a capability of interacting with object in more task-related manner. Well, what does that mean? So this is a collaboration with University of Karlsruhe, and there are humanoid robot there. So it's about planning how to grasp objects, but taking into account that you have two hands and applying a left or right grasp or a top grasp and so on. So it's a little bit difficult to see all the aspects of the research that we are doing just in this video. But the idea is that, well, if the robot cannot use its left hand to pick up the glass, it will remember that it has also the right hand, and it will be able to vary and use the capacity of its body to apply all these different types of grasps. This is still pretty simple, right? There is one colored or colorful object on the pretty simple background and so on. So in order to be able to do some of the vision-based techniques, we need to, or we needed to, this is a bit 2 years old work, we needed to simplify a little bit of the background. More movies to come about that. Let me see if we can go forward. So what are the challenges? Well, we want to work with complex scenes. We want a robot to be able to interact with new or previously unseen objects. And again, as we have seen, as we have heard from the talk before, how often do we really encounter things that don't look like something we have seen before? So familiar objects, if you want to call them like that. Uncertainty in pose estimation on rigid objects and so on. So I'll now go through all of these, how we addressed all of these in our approach. Now, the first thing, and that I think is also interesting, now when we look at something and we are not sure what we see, so a case like this, we don't know whether these two bottles, well, from my perspective or from my point of view, whether these are glued or whether these are two objects and so on. Well, we do have a tendency of looking at things from different sides. Doesn't really require almost any energy to use our body to get a better perspective of the world. That's one thing. The second one is how do we then basically use the knowledge? So if these are the two bottles that I have, or if the bottles have labels that I have never seen before, still the shape of the bottle is such so that it makes it as a familiar object, and I can easily perform the recognition. So then one thing we would like to have is a robot that can move its head, so can kind of mimic the neck and eye motion of a human with saccades and pen, tilt, and so on, motion in the neck. And this is what we have. So this is a humanoid robot head, and what it has, apart from having then the ability to move and look at things from the side, from different sides, it also has 4 eyes. So it has 2 stereo setups, 2 for the peripheral vision and 2 for the foveal one. So for the foveal one, cameras have about 14 degrees of opening angle, and peripheral ones have about 60. So the images that you see at the bottom are the ones from the foveal cameras. So what the robot does, I'm going to tell you about the technique a little bit later. It observes a table with a couple of different objects. Now the background is a little bit more complex, and there is a little bit more complexity in both the shape and texture of objects. So what it does, it uses the eyes and the ability to be able to focus, so tend and focus on things, to build hypotheses of objects with basically no knowledge. What does that mean? Well, the robot doesn't have a database of any of these objects to start with, but what it has a process for so-called figure ground segmentation. So what we assume about the world is that most of the objects are usually placed on planar surfaces and that they stick out, okay? So there is some 3D aspect to them. What more we can assume is that objects are rather simple in shape, so there are not big and complex holes or anything like that. And in most cases, they also have some form of a uniform texture on them. So I'm not talking about a single color, but I'm talking about statistics on colors that is more or less uniform. So what is happening here is that the robot moves the head, attends to different things in the environment, and the white thing that you're seeing that is growing around objects is it builds a hypothesis of an object, right? So it uses 2 cameras, so it's in 3D, extracting the object from the background. And the only notion or the only information it has here is, again, there is the object is placed on a frontal surface or on a planar surface, and the statistics in color, and also it doesn't extend infinitely in depth. It also has some convexity, if I can say like that, to it. And I think it's interesting to see that only with very few assumptions, what we can do, we can perform a pretty nice object detection, and we can do it in 3D. And the interesting thing is also here with the cup, that how the handle of the cup is detected, right? So there is a hole, you see here now, there is a hole which does not belong to the object. So even some convexity or concavities can be detected. Now once we have this, we have the access then to the textural information. We have the aspect of segmentation in 3D. So if we want to build on processes, further processes on this, we can, for example, fit some form of a generalized model to it. superquadric or whatever, or we can just use a point cloud that belongs to this object or to the region that we have segmented, and then perform some grasp planning on this. Now, and we didn't really need to store anything. However, if we would like to make this to a process where we incrementally learn what we would need to do, and then also in terms of interacting and grasping, is that we try to apply certain grasps on this particular object and then see what works and what doesn't. But just to tell you a little bit about the modeling, I'm not going to go in all the details. So we have M represents measurements, which are positions, disparities, and colors in stereo images. And L is the labeling, where I said we have 3 hypotheses, which is foreground, background, and flat surface. So we are setting up basically a probabilistic model for this, where the joint probability is given in pretty Bayesian terms. And we have distribution for these 3 different measurements, again, positions, disparities, and color. And what we are trying to solve then is marginalize really over all labeling. So we are trying to find the most likely explanation for the measurements given our model parameters. Now, just to tell you a little bit why this is a hairy problem, it's a little bit hairy because the number of combinations of labelings given the size of the image is 3 up to the size of the image. So this is what we would need to, let's say, marginalize over. But in the paper that is cited up here, we have actually shown how we can change the formulation of the problem a little bit in the framework of expectation maximization, and do this actually with the help of, again, belief propagation in real time. So obviously, there are ways and processes, but what is important to say here is this is not some form of heuristics or something like that. We are really trying to solve the problem in a kind of hypothesis generation and confirmation manner using then the current state-of-the-art methods for probabilistic inference. Okay, so let's say that we are able to do that, and now did we cheat here a little bit? Well, of course we did in a way, because when I showed you the image of the image with all the suites, you know, there were like many objects just basically thrown in the scene, covering each other and occluding each other and so on. And to some extent, not in all cases, but here we have a single object where the texture is pretty different from the background and so on. And then you will see also that there are some occlusions where we still manage to, let me see, extract the object. So in the case of the duck and the sugar box is coming there. So, well, here you see a little bit of occlusion, and now here, so the head of the duck is occluding the object, so we are not taking the duck's head in the model of the box, and then vice versa here. So even if we have frontal and backward basically occlusion, the method is able to perform. However, there are a little bit different or more difficult cases, such as, for example, this one. Let me see if that will work. No, okay. So what we can look at are ways of how a robot can build, I think it's this one, how a robot can maybe interact with the scene to confirm hypotheses that are visually impossible to solve. So if you look into an image like that, you would say that, well, it looks like there is another object behind this one, right? Yes, no? Yeah, it looks like that. And this is very difficult, right? It's very easy for humans to say, but you know, the object behind is brown, and I can tell you that when you extract colors, there is basically almost no way of either seeing the difference in color or even seeing this edge here. It's all about thresholding, but it would be very difficult to say. So if a robot sees something like this, what we would like it to do, and there is some uncertainty, and the uncertainty can, for example, come from shape, or even if we have the right thresholds from the texture. The idea would be to let the robot interact with the scene and confirm or disconfirm the hypotheses by, again, moving things around. Again, an easier thing might be to just look at things from different sides, but when we cannot do that, we apply actions and try to, I mean, humans do that also, maybe not as slow as a robot, but we can change the scene actively in order to provide a different starting point for our process of segmentation. Now, this is something that we have been working on and looking into what kind of processes or what kind of interactions would be necessary for a robot to be able to deal with. I think my computer just froze. We needed a 5-minute break anyway, so I was thinking to do it after 45 minutes anyway. So
don't worry, you have to reboot?
No, I don't think so. Let me see. It's something is coming back, but let me see. It's not coming up on the screen. I can see it here without the problem. Let me just do that.
Yeah, let's try that.
Maybe it wasn't my computer.
It wasn't your computer, I'm sure.
Let me see. I think it's coming. Yeah, it's going to be.
Okay, good.
Hopefully.
Yeah, always when I stand here, things work.
You scared it off.
Yeah.
You see? Good. You're scary, Paul. Okay, so what we could do is try to then learn how to detect objects, but with the use of action. So there are, again, these assumptions that we can make. An object is likely to, at least locally, have some coherent appearance. Shape is not too complex, as we said. And then when the activity is used, we can consider rigid objects and then assume that features on them will move according to some rigid transform that we can estimate. So now part of, from using the appearance and disparities I have shown you in the approach before with the Markov random field framework, we can use that and then add on the motion cue and then develop a system that looks something like this. So it's again hypothesis generation and verification process, again in the Markov random field kind of manner. But in order not to go through all those details, this is how it looks. So we can start with an assumption that there is one or more than one object in the scene. And then we confirm first the hypothesis that we have, and then we can say something about the statistics. So we can say how likely it is that this is one or two objects, and so on. And two things we can think about again are basically the distributions of the texture and the shape. And if there is some likelihood of these two not being of what we commonly are used to see, we can initiate the interaction process, such as, for example, pushing, and then seeing whether one of these or part of this, what was considered as one object, moves differently or doesn't move at all, and so on, and then update the hypotheses about how many objects there are. And this is really, really interesting because there are many other things that we can do. We can, by pushing, also understand something about different types of affordances of objects, so whether they roll or whether they translate, in which poses they roll, in which poses they translate, and so on. But what I'm looking back into and what I wouldn't want you to forget about is what is the learning framework that you use. Again, what is the dimensionality of your problem if you rely on the use of, let's say, appearance information or motion information rather than having a geometrical model of the object. So, and this is what we don't have here. So we don't have notion of cylinders that we somehow fit to the reconstructed point clouds or anything like that, right? So they're just groups of pixels that are coherently moving together, and that we are.
But these themselves as template are priors to the system or not?
No, they're not. I mean, the only hypothesis that we have is the foreground, background, and the planar surface, right? And then what we have is that once the first segmentation has been done and once the first model has been built, we fit the parameters to 1 or 2 or 3 or whatever hypothesis that we have that we call the foreground hypothesis. So in the first approach, we had only one foreground hypothesis. In this approach, we now allow that there are several foreground hypotheses, right, where we then extend. So for now you have even more labelings, right, because your labels are not anymore only 3. Again, we are not using this information in a process of kind of, then storing and understanding this information long term, but that would be one of the approaches that we would be looking at. And then, so for the sake of my computer not dying again on me. Okay, now it did. Good, excellent. Anyway, I'll show you this movie and then I'll restart my presentation. So it's a movie where it's a pretty long one, but this would be the first hypothesis. So we just assume that there is a single foreground model on the table. This is the head, just describes how many degrees of freedom there are and so on. And then we might have some kind of a weak hypothesis that might have been initiated either by humans saying that, well, there are actually 2 objects, now you need to find the most likely explanation for these 2. Or you might say that you have detected just 2 complex textural objects and so on. So that's the first hypothesis. And how we push, we basically go and push in the middle. And here we were lucky, right? Because pushing in the middle was basically moving mostly one of the objects and a little bit less of the other, although the other moves, right? But that's the interesting thing. So even if there was a more complex motion, the features on these 2 would be moving differently, and then the hypotheses of, well, can be made. So this is so the previous image was from one of the stereo cameras, and this is camera on the side. So you also see, but it's the same video sequence. So you just see how placing the camera somewhere else results in much, let's say, lighter image and so on, and the scene looks completely differently. So you basically would need to apply. Let's say a longer pushing action in order to be able to see the differences. So it depends also from where you view things. Okay, so I'll stop this. It's a pretty long movie. And I'll go back to my presentation. I was somewhere here. Okay, but what can we learn from humans? And how can this information be used? Now, this is our results from one of the projects that ended up last year. It's called GRASP, and this is collaboration with Heiner Deubel in Munich. So he has been looking very much, he's a psychologist, and he has been looking for quite some time in overt and covert attention of humans. So what is that we look at under grasping action? So what is that we look at when we are to grasp things? And there is very, very little work on this. Some of the things that we have done during the 4 years have actually generated pretty much attention. So the interesting thing here is that we have human subjects that are looking at a couple of different objects, and I think that you recognize them. We use the exactly same objects that we then use in robotic experiments. So they are asked to grasp an object from side or from above. So having so-called, in robotics terms, top grasp or a side grasp. And their eyes were tracked. And what you see here are so-called heat maps. Heiner called them heat maps. So this is what you attend to prior and during, applying a grasp. And it correlates very much to where your thumb is going. So you're kind of putting your eyes at the position of the object where you're to put your thumb. So there is a leading finger, thumb, and then there are fingers that kind of just follow up and then compensate the object. Now there is a lot to discuss and a lot to think about. So what kind of prior knowledge we used here, how are we affected by the thing that we know what we are grasping. Again, does the type of grasp, so if you are instructed to grasp with 2 fingers or use the full hand, affect the way we look and so on. So there is some subsequent work on that. But in robotics community, experiments like this have actually inspired people working with machine learning and computer vision to try to use these heat maps to define or design, again, features that are good for grasping. Now, again, we know that there are features, Viola Jones and so on, that are plausible for finding faces. Shouldn't be also easy to then define features that are good for grasping. So what did people do? This is work from Saxena while he was at Stanford. So he took a built a big database of synthetic images of objects. That's the first line up there. And then he went through a process of marking or labeling those images. That's what you see in yellow, which are basically good points to put your fingers around on each of those category or instance of objects. So, for example, for the book, as it would be for the bottle, the best thing to grasp, or the best point to kind of visually servo on, would be a point that is close to the center of the mass of the object. That would kind of result in a best or the stablest grasp. For a plate, which you see in the second image, you would be picking up things or applying your fingers anywhere on the rim of the plate. So any point along that circle would be okay. And so on. You see for the glass and so on. And there are also on some of these objects, some of these examples, there are also several other grasps that might be good, but this was not marked in the database. I think that for example, for the glass, there might be also points on the rim of the glass. So you would also sometimes pick up a glass like that. But what is interesting is that, again, now we are doing something that is very strange, right? Because I just told you a couple of minutes ago that on any object you can apply infinitely many grasps. Not all of them are optimal, or not all of them are good, right? They might be requiring support from your other arm and so on. So if you do this, and you feel with your tactile sensors on the hand that it starts to rotate, you will use your other hand or arm for support and so on. But all this knowledge has been taken away. So the only thing that we have is then marked objects, and then the idea is, okay, let us again look at the small windows, so local information, no global information. You will just in a couple of seconds understand why I also show you the red sculpture. So again, thinking about the patches that are good to grasp, so what they did, they took small windows around those good points to grasp, and basically looked into the first, second order relations between first or second order filters and so on, and tried to make then a classifier, or they made a classifier that in any image, so if you get an image of a bottle like that, for example, or a glass, are able to vote for every single small window in this image about the likelihood of that being a good or bad grasping point, right? So for every small patch in the image, you will get some likelihood. But for most of the things, if the background is completely uniform or single colored, you will not get any response. So the likelihood will be 0 or very, very low. However, for the things that are somehow similar to things that you have in the database, there will be a higher likelihood. And there will be no single point with the highest likelihood, right? So there will be a likelihood map, and then you would be doing some majority or whatever voting there in order to find the area in the image where that grasping point is most likely to be. Now, these are images after they have been processed on several stages in terms of finding then the likelihood landscape and then looking into points that are locally or have lots of support from the local neighborhood on being good points to grasp and so on. Now the problem is that there are two things we haven't taken into account because we are working just with 2D images, right? We haven't taken into account the global shape of the object because there is no notion of global shape, right? That's the first thing. So we know that this might be a good thing to grasp, but maybe equally well that the rest of the body is such that the robot cannot at all, due to its size, for example, pick up this object. The second thing is that there is no notion of 3D, and the robot is supposed to act on things in 3D. So it needs to grasp an object. So there is, what I'm trying to say, that even if we are able to find good candidates to interact with in an image, there is still lots of processing to be done before a robot can go and then apply this grasp on that particular point in an image. We have done some subsequent work and looked into how these local patches can be integrated with some global shape, both in 2D and 3D. So we have looked into, as it says here, so-called shape context, when we actually don't look only into a single patch on the object, but we also look into how that patch relates to all other patches on the object. On the object. And now the difference between this and the first method, where you just look into a single patch, you need to again use some form of segmentation. So you need to build a hypothesis of an object in order to be able to find a curve and then relate the points on the curve to each other. Now, is this a viable way of solving things? Well, it's one way of solving things, and I'm just trying to give you an idea that why this problem in terms of grasping and object manipulation is still being very vividly researched in the area of robotics. Now, I think that most of you in the audience know about Yarbus experiments from 60s and very much looking into human attention, what humans look at, what they concentrate on when they are given a certain question, and how our question or the task that I have been talking about relating to the image that they are looking at. Attentional cues and the whole work of Gestalt, also how we group and how we segment things, have been also used very much for building artificial systems that are working so-called bottom-up, right? So looking at single or several images, grouping edges or things that look alike in color together, and then performing or detecting so-called saliency in the image, so trying to find something that somehow sticks from the background. And this is following some form of a biological aspects of how it works in humans. Now there are different models also for both principles for grouping and figure ground segmentation, how and what to group together. Again, in our approach, we have been looking strictly into color, and we have been looking very much into this aspect of convexity and things being close to each other. But there are other aspects that are more or less geometrical. However, and as we have also heard in the talk before, these bottom-up processes are probably not the only thing we do, and these are of course not solving the problem, especially in the area of robotics, because what we do have to start with, or what the robot has access to, is the task, right? So in most cases it is asked to do something, bring me my cup or finding something to drink from and so on. So part of our research has also been looking into how we can have different models for top-down attention. So how can we use task, context and experience in the process of segmentation. Not going to talk very much about that. There is a paper from 2010 in IJRR that talks about that. But what I want to talk more about is more this kind of like developmental approach to grasping. So what to represent and how can we then go from no knowledge to some knowledge that then we store and perform inference on. This is other work that we have done. There is a more recent paper. I'm going to give you reference to that looks in the process of how a robot can then acquire these competences. Let me see if that will play, hopefully at some point. How can a robot build incrementally knowledge of what and how to grasp without really understanding anything about objects. So what we have here are two objects on a background, and what the system does, it uses different types of grouping principle in order to find a candidate of things that somehow, things, I'm calling them things because there are no notions of objects that belong together. So it's grouping things that are coplanar or things that are again the same in color. And then what it does, it has kind of like a mental model. So it accesses the ability to interact with the object. So how did we model this? What we did, we use a simulator. So the robot doesn't know what it looks at, okay? But in the simulator, we have a full model of the object. So we also model geometry and dynamics. So what the robot can do, it can try to mentally test, or it mentally tests different types of grasps on combinations of features. So it doesn't have a notion of the object here. But then what it can do, it can test it in simulation, and then it can use this information of having a stable or not stable grasp to put some statistics on how combination or combinations of certain features result in better or worse grasps. So it's only using the simulation for generating the statistics on the actual features that it can extract without really the notion of objectness. So one can think that if we have, this is extracted again directly from stereo information, and the things are combined or integrated based on some Gestalt principles. But the idea is that if the robot really doesn't act or interact with those objects, it's very difficult to say that, for example, a circular or a revolute surface affords this or that type of grasp better or worse. Again, two parallel, two planes that are parallel also afford certain type of grasp and so on. So this is more kind of like a developmental approach, but again, in order to be able to, for the agent to get the reward, it either needs to come from a human, so human says, no, this is not what you would usually do, or it needs to have some form of a simulator that can provide this for the agent, and this is the second thing that we did. We have continued with this work. We also have a recent paper again in IJRR, which is now going from small patches that were two-dimensional to detecting surfaces. And the question is whether the next step is going from surfaces to objects, and then trying to find the statistics for how do surfaces in single objects usually relate, what statistics on that. It's well, to see whether and to what extent we want to continue with that, but that's the whole idea. So we go from basically detecting points of using points and combinations of colors, lines, to 3D line segments, to 3D contours, and then again getting surflets. Drawing a parallel. So in both of the approaches that I have shown you, in one way or another, we generate some hypotheses about things or objects in the world with no prior knowledge, either by the process of grouping that is based on the Gestalt theory and 3D reconstruction and so on, or more in the kind of like probabilistic framework with hypothesis generation and confirmation. The idea of both is then, with no prior knowledge, to get some notion of input for the grasping system, generating grasps, and then going back and learning more about how to then grasp objects we haven't seen before. But what is a good grasp? I think this is a legitimate question to ask. And it depends very much on, again, going back to the task-related aspects, what we are supposed to do with the object once the grasp has been applied. Now, if we are just to move an object from A to B, maybe we don't even need to grasp it. We may potentially push it, translate it, or use another object to move it, and so on. If we are grasping or handing something over to somebody else, it's not really about the grasp. It's really about how much of the free space on that object we leave so that the person that we are handing the thing to can apply his or her own grasp. So how do we understand that? How does the task come back to the robot, and how does the robot that, for example, use imitation for the process of dealing with this problem really understand that it shouldn't mimic exactly the type of the grasp? And you see the difference also in the hand, but what it should be mimicking is the free area that the human is leaving for another one to take the object. So how can we encode this? The approach that we have taken is, again, a probabilistic one, where we looked into how we can exploit two things. Well, we started with modeling using very simple graphical model, which is a Bayesian net. It's a probabilistic model. And we say, okay, there are certain things that relate here. There is the object, there is the task, there are some constraints that the task poses, there are the effects of the action, there is the embodiment of the robot. So if you consider each of them as one state or one of the variables in the graph, the thing that you want to understand is then the relation between these states, right? So you want to understand the structure of the graph, what affects what and when. So does it really matter that the apple is red if the task is to pick it up and give it to somebody? Probably not. But if the task is to, for example, find the apple, the redness or the color of the apple might matter. So if the task was give me something to eat, the color will matter. So what we looked into is, again, a data-driven approach. So having a big database of a couple of different tasks with many different objects, with a couple of different robot hands, and then solve what is still an unsolved problem, and this is structural learning in Bayesian nets with mixed nodes. So some of these variables are continuous, and some of them are discrete. Colors might be discrete. However, the grasp you might represent in a more in a continuous manner. So how do we do structural learning in mixed Bayesian nets? So we have looked into, in order to then really solve the problem, we have looked also into different aspects of discretization of continuous data. and then use the classical structure learning algorithms. So you have, there's more work on that, so how we did that. Now, what has that resulted in? Let me jump a little bit through, well, let's say that again we go back to the robot that I showed you in the beginning, and now it has 3 different objects in front of it, and it might be given a couple of different tasks, such as, for example, to pour something from a bottle to a cup, or maybe just hand over an object to a human, or, for example, play with a car. The system looks pretty hairy here, but it's very difficult to put everything on one slide. So what is that we have? If the task is robot bring me something to drink, and it's really interesting how Moshe has also been talking about things, how we understand things. So if you, for example, say to the robot, bring me something to drink from, how that from at the end really changes the whole task. And usually, again, just doing the processing, the language processing is, again, not an easy thing to do. But let us concentrate on this one. So robot bring me something to drink, and what we would potentially like the robot is to look into the scene like this and then bring me a bottle of water, or well, something that it knows or has been labeled as a drinkable object or object class. So what we have is that we, to start with, have a probabilistic model that is then encoding not only then the aspects or the attributes of the features that we can extract from an image. It also looks into the embodiment of the robot, so what type of grasp a robot with 2 or 5 fingers can apply on the object, which affects very much the type of grasp it can execute. And then it also looks into how to do that in a very well, realistic scene. Still, it doesn't look like that sweets scene, but it's getting closer and closer. So what the net result of the whole process is, again, you can read about the individual steps in our papers. But the idea is that the robot generates heat maps, now not in 2D, but in really 3D. So it's given the task of bring me something to drink, And the idea is that around each object in the scene, so we assume that some form of segmentation has been performed, or that the category recognition has been done. Around each object there is a sphere, okay? And what you should visualize it at or understand it is a probability distribution that tells you something about both the likelihood of that object fulfilling a certain task, but also encoding in itself the direction of a grasp that it should be applied on an object for that particular task. So white is a good grasp and black is bad grasp, and everything in the middle, like red or dark red, is then well, close to bad than to good. So in the case of glass, for example, and if the task was to drink from, the black says, well, if you are to drink, or you shouldn't be picking it up from above, because you are obscuring then the opening. And from the bottom, it's commonly that you don't do it because it's the glasses are commonly put with the bottom on a surface that holds them. So the best grasp that you can apply is in the region that is then, you see, rotationally invariant, basically around the vertical axis on that object. And this is also something that you see, it's a little bit difficult for each object here. So the highest likelihood for the objects that I can drink, it's, I think, this bottle and that bottle, so that's yellow. I don't know if it's easy to see, but everything else is red or black. So you get the information that, well, there are objects, okay, but these ones you should not touch because they are not fulfilling the tasks you are supposed to execute. And by processing then also the whole scene, we can also get more information about, and this is what you don't see here. So even if the grasps on the bottle are pretty, the probability of grasp is pretty high on this side, you can integrate it with the objects that are close to that one, and then have a lower probability, and then just use probability of, so this is now integrated with motion planning, so you can use that information easily in your motion planner. I'm not going to go into details. This is how usually the segmented information looks like. So there are some spurious pixels. There are things that we cannot match because we don't see everything. Now with Kinect, some things do get easier, but some don't. Now you see examples here of a tool use, for example. So or pouring, for example, so you don't pour with a screwdriver, but what you do, what you use it for is tool use, while you don't use cups and bottles for tools. So now this is just a little bit magnified information or magnified result of what I showed you in the previous image. Good, nice. What are the challenges? Well, there are many. Now, most of the features and whatever kind of features we find and try to develop in order to disambiguate between things, so categories or object instances, there is always very easy to find another example that says, well, it looks like this, and the features are not anymore easily used. So, for example, what we are currently looking at is what kind of actions or activities a agent would need to use in order to disambiguate between a screwdriver and a carrot. Okay? And because visually these are very, very difficult to discriminate. What is also making the orange different from the ball, and even more difficult if the ball was orange. And then also the differences, for example, between a cup and a toilet paper. So the interesting thing now are the processes or the activities that we can use in order to disambiguate between the categories or instances of categories that would, again, confirm the hypothesis again. Think about using appearance and motion. I would also like in the same framework to have not only the pushing actions, but other actions, such as, for example, squeezing things, okay? So have information from the tactile sensors about how a screwdriver and a carrot feel differently when you pick them up or when you grasp them. How can we do that, and how easy is to use tactile feedback for doing this? For quite some time we have been working on grasp stability assessment with the use of tactile feedback. So humans are so very good in detecting, and we are doing that almost instantly, slippage. And then using a corrective action not to let the object go basically from the hand. So what we have looked at is how we can integrate both tactile and visual information in a, again, probabilistic kind of framework with stochastic models, looking into the things that slip from the hand. Sometimes it's very difficult to do it only based on vision, because once in the hand, the object gets covered by the hand. So tracking, plus that there are very high velocities and dynamics on how the object moves. So we looked into the integration of these two. So just to give you a little bit of an idea of how that's done. Will that hopefully play at some point? No, okay. Um, pu- 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 So just to show you the basic idea. So let's say that we know the model of the object that the robot is manipulating. So we have a full geometric model and we can track it. So we can estimate the pose of the object in the hand. And we can also read hopefully this is playing. We can also measure on the tactile matrices on the finger the contact or the contact with the object. So if a grasp like this is applied on the box, there is a pretty high probability of this being a stable grasp because the robot has tried it before, so it has, in a kind of like a developmental manner, been picking object up and then looking whether after lifting it has stayed stably there. So then the hand moves a little bit, there is an offset or somebody moves the object and you see that the stability changes, right? And compare it again with the bottle. So here in the middle is very stable, but when you move down or up, the stability will change. And then maybe there will be areas, like in this case here, that the robot hasn't explored. And then I'm always asked the same question. So shouldn't be symmetric. So if it knows that on that other side it's more or less stable, shouldn't be the same on this side. The problem is that it didn't explore, and we did not assume that the objects are symmetric. And the reason is that maybe the mass distribution of the object is not uniform. So it might be that one part of the object is heavier than the other, or that the liquid or the mass that is inside changes differently once the object is picked up. So we expect the robot to basically explore everything. So we can, with a very simple model, we have both the temporal and the one-shot learning method with SVM and then with HMMs, look into the likelihood of, if I grasp here, how likely it is that the object will remain in the hand. And some subsequent also pretty cool experiments that we haven't, or results that we haven't been talking about, that we haven't planned for to start with, is that certain actions or grasping at certain parts can actually result in an effect that might be also beneficial. So let's say that the robot is to change or rotate this object, right? And rotating it, it might be grasping it and then putting it down and so on, which might require a set of actions to be planned. But if the robot applies a grasp here and knows that the net result of this is not necessarily unstable grasp, but a grasp that results in rotation of the object, then it can use this knowledge to then generate different types of activities if that's the reason. And in many cases, this might be a desirable property because when it comes to tool use, and this is what we usually do when we use tools, we tend to pick up something and then, like a pen, change the position of the thing in the hand in order to be able to manipulate it in a certain way. Now, I'm not going to go again into details. If there are questions, I would prefer to go through them, but just to give you a little bit of an idea or a flavor for what we are doing right now. We are integrating the probabilistic inference framework for task-related grasping with online stability estimation. So this might be, let's say that the robot says, okay, I'm going to try some of those infinitely many grasps and asks the Bayesian net whether this is a good for a specific task. So pouring from the detergent bottle, looks into that probability distribution is black, so no, this is not a good grasp, try something else. Then it tries something from the side, and the Bayesian net says, yeah, this looks like something you should be using for this task. But then the subsequent thing is to then start to execute the grasp and close fingers around the object. Now, due to uncertainty in pose estimation or due to uncertainty in kinematics and so on, it might be that the grasp actually did not happen here, so encompassing the center of the mass, but there is a small offset. And you will see that, or you will feel that on the tactile sensors of the hand. Now, if you also have a tactile-based classifier and it ends up to be in the red zone as it is here, now this is evolved probability distribution map, it says that, well, from what I feel, so not from what I see, from what I feel, you shouldn't be grasping this object. And just for the purpose of confirming it, we tested and it slipped just because it wasn't having the right contact with the object. So we can play with that and we can find the grasp and try. So prior to actually moving the object from A to B, we can try to grasp it at different points in order to get something that is more appropriate for the grasp. But the net result of the whole thing is also asking ourselves what can we learn from the fact that robots have these different hands and that we need to train things for different hands. What can a robot with completely different type of kinematics actually learn from human, and how to extract this information? So one of the current projects it started just a couple of months ago is to try to look into how we could find some form of a common space or a way of comparing human hand with different type of structures that can be more or less anthropomorphic and structures that can be more or less dexterous. So what is the measure of goodness? How good hands can we build, and what can those hands do, given that they cannot by default have 25 degrees of freedom, or even 12, because they would need maybe 12 motors and so on? Or how can we compare human hands with different types of other actuated hands? And one way of doing that, of course, is, and this has been done so far, you build a hand, or you build a model of the hand, and then you test it in simulator with many different types of objects and so on. Our approach was, of course, to first try to generate and see what kind of grasps humans commonly do, and this is what we are now looking at, and we will be generating a huge database of hands interaction with objects in everyday settings, okay? And we are doing this both with Kinect and potentially with stereo. So if you think again back to the washing the dishes scenario or a movie, this is exactly a movie that we would like to look at. So human interaction, human hand interaction with everyday objects in very many different tasks. Just try to understand about couplings between fingers, which fingers are support fingers, which are kind of followers and so on, and use this information to build some form of a space or understand the dimensionality of that manifold, and then use different types of dimensionality reduction techniques, in this case nonlinear, such as Gaussian processes and so on, to try to find a measure of goodness, to what extent some other design, kinematic design, of a hand covers that space of human grasp. There is actually a paper coming out in Transactions about some initial work, Transactions on Robotics, some initial work on this, where we actually generated, if I'm not mistaken, 35 different types of grasps with 5 humans, and look into how we can define a space, in this case just two-dimensional, for the purpose of visualizing it. It looks like this, with nonlinear dimensionality reduction techniques, with the requirement, with some constraints, and this was that the grasps that are similar, or grasps that are on similar objects. This is a temporal trajectory for grasping a cylinder-like object. This is more with only using the 3 fingers and so on. So we have tried to build the space so that the grasps that we think are visually alike or kinematically alike end up to be very close to each other, and then look into the techniques that can project with any 5-fingered robotic hands. This is a Karlsruhe hand, and this is a new prosthetic Michelangelo hand from Otto Bock. So project it into that space for exactly the same type of grasps and see what they do, what can they actually cover. So the idea then there is to deal with the problem of really designing a hand that is not necessarily exactly looking like a human hand, but that is covering a certain type of grasp in some x-dimensional space that is defining the space of actions that the robot is supposed to do. So if the robot is supposed to wash dishes the whole day, it would probably need different degrees of freedom than if it's driving a car the whole day, right? And since we, again, still cannot build hands that can mimic exactly the dexterity of human hand, this is one viable way of approaching the problem. This is also very interesting for the developers of hand prosthesis, because this is also a big problem in hand prosthetics. So which degrees of freedom do we actuate? And the constraint there is that the hand actually needs to look like human hand. So there are some parameters that are, so to speak, predetermined there. And what we can show with our technique is that the space that we learn, or that somehow represents human grasping, if you take any 5-link manipulator, so you build something that has 5 fingers, but it's not anthropomorphic, right? So what it would do, it's maybe very dexterous, so it can do many things that a human hand cannot do, but it covers only a small portion of that human space. So what we would like to do is to build a manipulator, right? With 5 fingers, but maybe with less links or more links on some fingers, that is covering as much of this area as possible. And just to end up a little bit, these are some of the things that we are looking at right now. Maybe this will play now, which is related to dual arm manipulation and the aspect of pre-manipulation. So in many cases, this is pretty simple object, right? A spatula, and we would like the robot to make pancakes. So first it needs to take out the spatula, but it's very difficult, right? On one hand, it has the sponge because it does the dishes whole day, and on the other hand, it has 2 fingers. It's impossible for the robot to use these 2 fingers to pick up a flat object. It's really, really difficult. And you can go home and then try to go around for a whole day and just use 2 fingers to do everything that you commonly do every day. You'll see how difficult it actually is. So the one aspect of this is what form of pre-manipulation or pre-action do we need in order to that pre-manipulation result in effect that then affords the next coming action, such as this grasping, for example. And now we are here using redundancy of the robot, but we are also using something that humans in some cases do and in some cases don't, right? So in some cases we will be pushing with one hand and picking up with the other, but in some other cases we will be just pushing with one and then do the same thing again. And the other, let me see, I had one more, which is a little bit more difficult, and that relates to the problem of dealing with non-rigid objects, cutting Swedish bread. Maybe it's even more difficult to do it with Spanish, I don't know. It's not that flat, right? So the idea is a robot that has picked up a knife, and now it wants to put this thing into pieces. And this is also something that requires lots of both tactile and force-talker feedback. But the interesting really issue here is the object representation, okay? So this piece of bread, or 2 pieces of bread, end up to be 4. So this is one problem. So how do we represent the state of the object? But even more interesting is, for example, chopping an onion. So onion going from a rigid ball-like shape or to something that is chopped. So how does the agent understand that the chopping really brings the objects from one state to the other? So this is just kind of like an add-on, something that we would like to look at for the next couple of years. So a little bit more complex actions and the effects of these actions that can then be used to test different affordances of objects. I think I'm going to end up here. Let me finish this once. And I think this is the last one. I just want to thank my collaborators and those that financed me and still financing me. Okay, I'm done.
Great, thank you. Dimitri? All right, Dimitri claimed he is faster than me. Bring you around the microphone.
So 1.5 hours. I did it in 1:40. This is it's good.
Working. Right now. So questions? All right, that's a good start there.
Oh no, I don't know if I want to be asked that question.
Hi.
Hi.
Well, it was. Is it on?
Yeah, I hear you.
It was really a beautiful presentation and very encyclopedic. I feel like read the Oxford English Dictionary of robot grasping. But the one thing for me always stands out that I'm wondering how you feel about this question is that when you go from robot grasping to human grasping, it's really a qualitative jump. And so as you quoted that Simon talk, the human has all the degrees of freedom and then lots of special purpose things like skin and lots of tactile sensors. And so these grasps that are sort of designed for certain things like cylindrical grasp, pinch grasp. And so there's a sort of space that the human lives in and a sort of space of things that the human can do that's just very, very different in ways. In some ways it's more specialist, but in some ways it's more general than the robotics. And looking from outside the robotics into robotics, I see particularly with your bread example, you're trying to do, people like yourself in the robotics are sometimes trying to do something with sort of one hand behind your back, like try to cut the bread without holding it, with one eye from the table. And so do you ever feel, what do you feel about that? Do you feel like, look, I have to get the grant money and go on? Or do you feel like, boy, we won't get anywhere until we somehow jump into anthropomorphic spaces? I'm just curious. It's beautiful to learn all these things, but I'm just wondering how you feel about, is there a gulf between the capabilities of the anthropomorphic system and what lives in there, and then the capabilities of your standard robot system and kind of the techniques live in there? Is there a sharp distinction there, or are we moving towards there? Just some comments on this distinction.
Whoa.
Thanks for this lecture there.
I completely understand what you ask, and I don't know whether I have sorted out my feelings about everything you have asked me about. So the first thing is whether and to what extent we should be mimicking humans. I mean, one thing is that everything that we have around us has been built for this body, okay? So most of the things we would expect robots to interact with have been made for this, right? And I think that, when we, a couple of years ago, made a study to what extent people would like to put different types of barcodes and so on on their walls, just in order to be able for the robot to understand in which room it is, no. People don't necessarily very easily want to change their environment in order to make it, easier for these artificial systems. And I think it's like that even for elderly people. Now I actually have a project which is building different types of homes in Sweden for elderly and disabled people. And even there, they want to kind of like have a minimum change in the environment in order to still feel like they're not living in a hospital or something like that, or that the things that are moving around are conveyor belts and things like that. So from one point of view, we cannot expect that the environment will change very much. So these robots will need to interact in natural environments. Now, whether they should look like humans exactly, no, I don't think so. I think that it should be really, really clear that, you know, what is a human and what is a robot. I don't think that the bodies should be the same and so on. But what I have learned during the past couple of years, especially in the area of prosthetics, right? There people are again not so very open to actually have a hook or something that doesn't look like a human hand. Again, I think that that will change, okay, because I think that as piercing has become a kind of a fashion thing, it might be also fashionable in the future not to look like everybody else, right? But we are still not there. So I think that potentially in the future we might be building things, robot hands or legs and so on, that people feel confident about of you know, having them, even if they don't look or act very, very human-like. Now, I don't know what the legal policies for having hands that are stronger will be and so on, but again, I also agree with you that in many cases we as a roboticist think, oh, okay, how do I commonly do that myself? And then I try to find or, you know, generate a process that will mimic my way of doing things, and I'm pushing the boundary of trying to do that with a body that it's nothing like mine. And this is exactly what was the example with the bread cutting. I mean, you know, we are not cutting bread with one arm or one hand and so on. But so this is a
Can I steer you a little? Like as you're doing that grasping, I'm thinking, well, as a human, if it looks vaguely like a cylinder, I'll just put a cylinder around it, and then I have these sticky fingers, I can just sweep in and grab it because I know the dynamic properties of
Precisely.
the fingers and stuff. I can just get away. I'm in a whole
Absolutely,
world.
absolutely.
Mathematics.
And this is why we now actually look into designs of hands that look nothing like human hands. I mean, you know, there are hands that have more fingers than human hands that look like octopus. You have hands that look like balls, right, and have kind of like a sand-like structure in them and can interact with the objects. All of that is good, but at some point you also want some measure of how good those hands are in situations where they are supposed to do this, that, and that, right? So I think that theoretically we still don't have a good way of comparing. You can have a data-driven approach, so you build a hand or you build a model of the hand and then you test it on a couple of different objects and so on. But we do that in a kind of like one-step thing, right? We look into the object and we assume that somehow the vision community has solved the problem of actually detecting it, right? And being able to then generate exactly that grasp. So the evaluation itself is considering just one of those processes, right? But not the whole process of from perception to action. And this is what I think is making the whole thing a little bit more complex, right? And this is why I think in many cases we are thinking human-like steps because we don't know anything better. But we don't in all cases, right? We have many developmental approaches to both let's say generating good grasp hypotheses and so on. And this was also one of the approaches that I showed you. There is no assumption about the object instance or the object category. Let us just have a robot try many different things, right? And then come to some understanding of what it can do with its own body, right? So in that example, those grasps that the robot generated were generated with a hand that looked very different from human hand, and it just looked into the combination of surfaces or surface points. Yes, it will give you some statistics. But at some point, you will anyway need to do a little bit more complex planning of, you know, what you are supposed to do after that and before and so on. So I think that, again, I don't think that needs to necessarily be taken into the whole process of drinking in the process of grasping. But I think if the robot is to pour, you know, make martinis or something like that the whole evening, that actually needs to play a role, because otherwise you will not, you know, be able to say, you come to a supermarket and you want to buy this or that robot. Which one do you choose? There needs to be some specification. Good. I'm done. No, I'm done. I'm not done. Okay, we can talk more.
So I think maybe infants, the way they sort of get the skills and also the right statistics is they grab an object somehow and bring it close in front of the eyes and then just play around with it for long amounts of time. Do the robots that we have today, can they actually employ this kind of strategy to generate the statistics?
Yeah, they can. But, you say they just do, and obviously we don't know how we do things. So I think it is extremely difficult, even if we put very simple objects in front of the robot. So what is that makes that robot, what would make me, if I have never seen this object before, okay, and I haven't seen anybody else using it, what is the drive for trying to do this? What is kind of guiding the whole exploration process? So I think that for some simple things, yes, we can do it, and we can generate lots of statistics, and we can integrate, the proprioception, the haptics, the force torque. It's not all that easy. We can do it, and I prefer to do it in a proper kind of manner with a well-sound model. And when you start to do that, because you want to do something with the model, you want to have a measure of how good your process is, right? There are still higher level things that are much more difficult to do. And this will need to come from somewhere else. And in my case, I think it was my husband that showed me this. Oh, did you see this new cool phone? It's not cool anymore. It used to be cool. But yeah, so there will still need to be some teacher for some things that are not easy to extract.
Good. Nathan?
I was wondering about what did... Sorry. So I was wondering what determines how close the fingers are brought together in the grasp. Is that something you estimate in advance, essentially like part of the pose, or is that something where you could use tactile feedback or assume objects are rigid so the fingers stop when they...
Oh yeah, you can use strain gauges in the hand, for example, so you have like the force feedback, or you can use, if you have better tactile sensors, well, you need something that also can estimate force to actually stop the grasp. So you can do some form of corrective movements. It's not so very easy because these are not very real time. But there is now in other European projects also being developed new sensory capabilities just for really having not only kind of like the pressure information, because this is what we have, but more torque and force information.
And say predicting it in advance from the size of an object, is that something that's typically done, or is it?
Yeah, that's you can this is what you do. So you use the size or the shape to control both the opening, but then also partially the closing.
Giovanni?
So, thank you for your talk. Beautiful,
yeah.
really. So, well, I have a question. So, when you look at grasping, of course, you describe very much the physical characteristic of the grasping, the perceptual and motor characteristic of the grasping, and of course, then you also discuss better embodiments, better shapes for the hand, and that's all. But at the same time, I think that for humans, of course, grasping is a very complex cognitive activity, not only the physical characteristics. And then, for instance, if you ask me to cut the bread, I can do that. I mean, if you change, if you give me a glove, I can cut it. So if you give me other tools, I can probably cut it. So my ability depends on the fact that I can really solve problems in very flexible ways.
You can generalize,
yeah,
based on your knowledge.
Also inventing new solutions, also understanding task representations a bit better. So this is also a part, something that you have shown with the structural learning part. So my question is, do you think that our advancements in the grasping will come from better sensory and motor and embodiment characteristics, or also from a much better understanding of the task or the outcome of my actions and or the goals of my action that then permit me to solve the problems?
Wow, I think that's a psychologist or somebody that has talked before me should be better in answering. Well, I definitely think that the experiences are kind of something that we use, because I mean, if I think about myself, how I do things, sometimes you do things with your eyes closed, right? So you are not necessarily using your full sensory capability all the time. You're using the experiences of the process, so how you did it before, and what you expect to be the outcomes of every single kind of individual task to do, and then you replan if something doesn't go according to the plan. But we have the ability of kind of, you know, at the same time, I think, using the experience, so the expected, we have the expectation on an action, right? And then as we heard before, when something goes wrong, then something else is kind of triggered in the brain, but that doesn't happen so very often, right? And then if it happens, I mean, it doesn't happen, well, what I wanted to say, if unexpected things don't happen very often, we don't have a tendency of putting a higher probability or higher weight. We do remember them, right? And we are maybe more careful or cautious. But I